Hello and welcome to today's webinar. This is Mark Plantier of Enercon Industries, and we'd like to thank you for attending Why All Films Don't Treat the Same. Please note that this webinar is being recorded, and you will be able to access both the recording and presentation slides once they are available online, usually within 24 hours. If you have any questions during the webinar, please use the GoToWebinar question tool. You may submit a question at any time during the webinar. We will reserve time at the end to answer as many questions as we can. Today's presentation will provide you with insights on the unique relationship between corona treaters and different types of films. Today's presenter is Tom Gilbertson. Tom is Enercon's Vice President of Application Engineering and has over 30 years of surface treating application experience. Tom has authored numerous technical papers and articles on surface treatment, including chapters in TAPI's recently published Extrusion Coating Manual. Tom is a frequent presenter at industry events including TAPI Place, AMCAL, SEMA, ICE USA, and the Flexographic Technical Association. In today's webinar, Tom will provide insights on the following topics: corona basics, how to use watt density to properly measure applied treatment levels, insights on dyne levels, their benefits and their limitations. We'll provide specific examples of how and why films may respond differently to corona treatment. We'll take a look at the impact of how higher watt density requirements increase overall system cost. And we'll wrap up with an opportunity for you to ask Tom your specific application questions. Before beginning, we would like to ask a question to our audience of what best describes your business. I'm going to launch this poll now. We'll let you answer it. You may pick from film supplier, film converter, film extruder and converter, industry equipment or material supplier, or consultant. We want to get an idea of what your experience are in the industry and why you may be here today. Got about 60% of the vote in. And we'll leave it open for a few more seconds. We're up to 80%. And it looks like we have 34% of you are film converters, 30% of you are film extruders and converters, 22% are industry equipment and material suppliers, about 5% are consultants, and about 10% are film suppliers. So we'll close that poll. And with that, I will turn it over to Tom to begin the presentation.
Thank you, Mark. Good morning, everybody. Thank you for attending this webinar. This is a very popular topic with us, and we're happy and very enthused to be able to present this information to you. It's information that is very important relative to your day-to-day use of surface treating equipment, and I hope you'll find the information contained in this presentation beneficial. So let's get started. So without respect to the type of equipment we're dealing with, so if you look at this slide, you can see we're looking at film extrusion lines, we're looking at various converting equipment, including things like digital film label producing and flexo film. Also, you could look at gravure, solventless laminating. You know, there's all these various technologies that surface treaters are used on, and the content that we talk about today is applicable across all these lines. This is truly a universal discussion relative to our industry. So again, without respect to the width, whether it's a wide web example or a narrow width example, the content is going to cover all of these areas. So let me ask a question to everybody out there. What is your expectation when you start your corona treater system? Now, I recognize the easy answer there is, well, I expect it to run. I expect it to generate corona. And I get that. But let's take that as a given. It's going to generate corona and it's going to start and operate appropriately. But then after that happens, what is your expectation? What do you expect the treater to do for you? Do you expect to see the same results every time you run film through it? Well, these are two core questions, and we're going to dive into the answers of those things as we move along. But I want you to think about those things as this program continues. To start with, we're going to look at how a corona treater operates, and we're going to get very basic here to start with. So we're all sort of starting from the same launch pad. So really, corona treaters, by definition, are pretty simple devices. They generate high frequency, high voltage energy that ionizes air. That's really what corona is. It's simply just ionized air. The parts of a corona treater, again, are pretty straightforward. You have a power supply that generates the actual energy to ionize the air. You have a high voltage transformer that takes the energy from the power supply and boosts it to a particular output in frequency. And then that applies the power to an electrode of some sort, whether it's a metal electrode, a segmented electrode like shown in this illustration, or a fixed with ceramic electrode, doesn't matter. And that then is mounted above a grounded roller that ultimately conveys the film and, of course, exposes the film to corona treatment in that gap. So that's really what corona treaters are, essentially just devices that ionize air at high frequency, high voltage power. So what happens when you corona treat a film? Many of you have asked this question of me over the years, and simply put, without getting into a bunch of high-end chemistry here, what corona treaters do is they form low molecular weight material on the surface. They add oxygen to the surface, and this is very important because, as you know, the films that we treat, whether they're polyesters or polypropylenes or polyethylenes, all those films are very non-reactive, right? They're not polar. When you just take one of those films that are not treated, and if you tried to take a magic marker and write something on it, you would find that you didn't get very good results, right? The ink wouldn't wet, let alone would it stick. And that's principally because the material has no polarity to it. It's very neutral. It has no activity on the surface. So the corona treater actually takes that and adds some oxygen functionality to the surface. It forms various positive, negative sites by adding and deleting components on the surface, and it oxidizes that film surface. And on top of that, it also does a great job of cleaning that film surface. So if you have a film that has a high additive content, like a slip additive or anti-block additives or various other things that are intended to come to the surface to give the film a certain characteristic, the corona treater can functionalize and sometimes remove those things in order to make the surface more usable for you in a converting application. So what are we looking at here in terms of the basic components of your corona treating system, and how are these components all put together? So the first thing we're going to look at is watt density, and then we're going to look at dyne level, and we're going to look at adhesion. And we're going to look at these three things and see how they interact or interplay with one another as we go forward. So let's take a dive into here, and we'll start with watt density. Now, as I've always said on these webinars, sometimes it's hard to do these calculations, math calculations in a slide format. So for some of you, hang in there with me. It's not complicated, and I'll try to do a simple verbal equation here too, just so you get a sense of how simple it is. But I would like to challenge the audience that in all of your surface treating applications, you should use watt density, if for no other reason, just to get a better understanding of how your material responds to a given setting of your corona treating equipment. And again, it doesn't matter the brand or whether it's a metal electrode or ceramic electrode. None of that matters in this case. This discussion on watt density is how much power per unit area of material going through the treater we're applying. And so what it looks like is this. You take a watt density calculation is simply the electrode width and number of sides treated and the line speed, multiply those together, and then divide that number into the watts. So in other words, let me do a quick example for you. If I had a 5,000 watt power supply, or 5 kilowatts, let's say, I had a 5-foot web and I was running 500 feet a minute. If I calculate that out, you come up with a watt density of 2. Now, to give you some context on here, most corona treaters dealing with pre-treated film in a converting application, printing, coating, laminating, most corona treaters are sized to run between a watt density of 2 and 3. Those are very common numbers that are used in our industry. Not all, of course, there's always exceptions, as many of you know in our business. But that said, a very common starting point for watt densities is that 2 to 3 watts per square foot per minute. Now, this calculation can be utilized across all product lines. So in other words, if you're in film extrusion and you are making a high slip content film, that watt density number might be higher because it takes more energy at a given speed just to sort of remove some of the slip additive and so forth and additives that are on that film. Now, once that film's treated and it comes to the converter and it's at an already elevated dyne number, well, just to bump that treatment or just to increase it a little bit to get it to be more functional may only require a 2 watt density. So these watt density values and dyne numbers do have connections, and we're going to work through this as we go through the slide. So let's talk about the dyne level, the watt density, and adhesion. A key element here that you have to understand is a dyne level nor a watt density guarantee adhesion. And I've experienced in 34 years of doing this, I've experienced, and many of you I'm sure have experienced the same, real life examples of this, to where you actually read an effective or a high dyne number, or what you would consider to be an adequate dyne number for a particular result, and yet for some reason the lamination came apart, or the ink didn't pass a tape test, okay? So there's other things going on here than just the dyne level, and particularly in film extrusion, or sorry, particularly in converting applications, there's a lot of chemistry interaction going on here. And so if your ink chemistry is a little off, or your adhesive chemistry is a little off, it may look fine. You may think, well, it looks good. It's metering on properly. That doesn't necessarily mean that it's going to give you the result you like. So like in this particular picture we have here, we show this picture where we have good wetting and good adhesion contrasted against an area where we, let's say, had the treater shut off, or somebody forgot to turn the treater on, a low adhesion, low wetting condition. And so that just gives you a stark example of what happens if you turn the treater off, or you think the treater's on, but it's not treating in a converting application. It's a great way to visually see what happens when you corona treat. But remember, the dyne level you have does not really guarantee adhesion. It's important that you use an adhesion test of whatever style that's appropriate for your application, and use that as a standalone value as you go through your test methods. The other factor that's involved relative to success in terms of surface treatment and dynes and watt densities and films are contamination and external environmental conditions. So let me give you a perfect example, again, one that many of you experience yourself. So you buy film from a qualified supplier. They provide the film all wrapped up, packaged, and they send it to you in a big long trailer. And that trailer, for a period of time, ends up also being a storage facility for you. So you park that trailer out in the back of the plant, and you take material from it as needed. During the course of that time, the weather changes outside, and of course the trailer's typically not going to be conditioned in a conditioned environment. And so whatever the condition outside is what the film is. And so in a hot, humid period during the summer, let's say, that trailer can get pretty warm. You know, it can get maybe 120 degrees or higher in there. And that can affect the performance of that film as you bring it out of there, put it in the plant, and put it onto the press. And so that environmental condition is a factor relative to losing your dyne number over time. And we get this question many times, well, if I buy film from a film supplier and he's corona treating it, well, why in the world would I need to bump treat this going forward? Why do I need to treat it again? Didn't we treat it the first time? And the answer to that question is yes, they did, and they did a great job. But unfortunately, the surface is dynamic on these films. It's not static. There are all kinds of things that are going on some of these films as they get stored. One of which, and the common thing, of course, is just additive blooming. And that blooming additive will likely reduce the dyne level over time. And so when that happens, and now you put that roll up on the printing press, for example, or on the laminator, now that surface energy is not sufficient enough to go ahead and convert. And so that's where the corona treater comes in that example, such that we refresh that surface and bump treat it to the desired dyne level for the next converting process. along the same lines, we're used to seeing things in a very linear fashion in our life, right? So let me give an example. So you know intuitively that when you drive to work in the morning to your office, as you're driving your car, you put your foot on the gas pedal and you increase the gas pedal and you go linearly faster. And you know that as you apply more fuel to the engine, the car just goes faster. And so it's common sense. People just know that's how it works. And there's many things in life that are like that, right? Well, in surface treating, there's a bit of a disconnect here because many people look at watt densities and they will say, well, if I apply a higher watt density, I'm always going to produce a higher dyne level. And while generally that's true, as the slide indicates here, that's not 100% the case, and it certainly isn't linear. Generally speaking, higher watt densities can produce higher dyne levels, but typically it's not in a linear fashion. And that can be very confusing and very misleading to folks as they go forward. So this is a very important point to recognize here. Higher watt densities, higher power settings on your treater don't always produce a dyne level that is commensurate with that higher watt density, or maybe I should say is commensurate with your expectation of what that dyne level should be. So carrying that thought forward, you cannot use a watt density to predict your dyne number. So for example, in an earlier slide we talked about, typical watt densities for corona treaters being 2 to 3 watts per square foot per minute. Many times I get the question from folks that'll say, well, if I apply a 2 watt density to a polyester film running a certain speed at a certain width, will that guarantee that I get 56 dynes? And the answer to the question is, I can't answer that question. I don't know. On average, in that example, could you get 56 dynes at that watt density? Sure. I think it's a reasonable expectation to have with that particular film and that particular condition. But I've also seen with polyester films, as an example, I've also seen other examples with similar watt densities or same watt densities, and you don't get that dyne number. So really, trying to predict an end result, in this case a dyne number, using a watt density is really not a good approach. A better approach would be to actually sort of map or take your existing product mix and do a bit of a qualification on some of this and give yourself, on products you run regularly, maybe customers that are quite important to you, big jobs, big important products that go through your shop. Maybe in those cases you want to line up your watt density values, your dyne level values, and then your peel adhesion values all in a template so that going forward, every time you run that job, this watt density should be in this dyne range, and that should equate to a particular adhesion result. If you do that, I think you're going to find going forward, the data you collect is going to be a lot more informative and a lot more useful for you going forward in terms of troubleshooting issues and just improving your performance to your customer. So why do films need treatment? Where are these variables that happen outside of our control? Well, they're kind of all over the place, and there's a lot of them. So first of all, film that comes to the corona treater is loaded with all kinds of baggage. Let me pick on just a few things, a few baggage elements here that I'm referring to. Some of it we've touched on. One of it is additives, and this is a significant one. Many times films we treat today have all sorts of different additives. They can be fillers, they can be surface surfactants, they can be colorants, they can be flame retardants, they can be anti-stats. There's just almost an endless array of different things that can be on the surface of those films. Some of those things are very benign. They don't affect the treatment, the material going through the treater whatsoever. Other things can be quite important to the success of treatment and may require you to operate the treater in a different way. So that's really what the treater is doing here. It's taking this film that's loaded full of these various things, and we're trying to correct for some of that as the film is surface treated. So if we take, for example, a slip additive, which tends to be something people are very familiar with, and we have a lot of slip on that surface, and after the treatment here, we're going to try to print it. We need to get some of that slip off that surface, clean it up so that the ink has a fresh spot to land on, which would allow wetting and then allow adhesion. So here you go. This is a perfect example of what I'm referring to. That slip surface is very low energy, right? It has no affinity for anything, no bonding, no wetting. In addition, you might have some dirt, debris, maybe some other surface contamination that just for whatever reason happens to be on that film. And so consequently, if you tried to take that film, bypass the treater and convert it, you would not be successful. That material would not be able to be treated. So what do we have to do? Well, the corona treater's got to take that surface, and we've got to remove some of these surface contaminants. We've got to bring this low energy back up to a higher dyne level or a higher energy surface to improve the bonding sites and improve its ability to grab onto an ink, an adhesive, a coating to give you success. So why is it then that with these watt densities and this treatment protocol that we have, why isn't it all the same? And so in this slide, what I'm trying to do is to give you a really good example of how the film and the characteristics of the film impact the end result. So let's walk through this. So our first example on the slide is pre-treated polypropylene. It starts at an initial dyne level of, let's say, 30 dynes or less. And in all these cases we're talking about here, we're gonna apply a watt density of 1.1 watts per square foot per minute to each one of these films. Okay, so the power that we're applying is the same. Same corona treater style, same power. When I treat pre-treated polypropylene with this watt density, we net not much of a result. At a 1.1 watt density, we might be up to 33, 34, 35 dynes, something like that. Not particularly encouraging. Same power density, but now I'm going to treat polyester. The polyester, if you note, started off a lot higher. The initial surface energy of that polyester was more like 40 dynes, and the end result of treating it at a 1.1 watt density is over 50 dynes, maybe 56 dynes. Let's take one more example. The last example on this slide is polystyrene. Again, we start off with its inherent dyne level might be around mid-30s, upper 30s kind of number. We apply the exact same watt density, 1.1 watts, and we are way up to 60 dynes or higher. Now, what happened? What happened, folks? What changed? The watt density is the same across the board, yet for some reason we got different results. How can that possibly be? What is wrong with that corona treater? And of course the answer is there's really nothing wrong with the corona treater. So the slide is trying to illustrate it. The point I'm trying to make to all of you there is that the film that you run, the various films you run, impact the end result of corona treatment. I kind of joke, many of you who are attending the seminar today, I know many of you attended some of these seminars I've done, and I kind of jokingly say in these seminars from time to time, if you want the best corona treater ever, I mean the best corona treater, the best performance out of your corona treater ever, always feed it quality pre-treated film if you're in a converting application. And that will guarantee you're going to get good results all the time. And you can see from the slide why I say that. Films respond differently to the same level of treatment. And so you can see also where the confusion lies on the shop floor. Let's take the three examples. Of those three examples, we have a 56-inch roll of this material waiting to be put up on a machine. From 10 feet, or for that matter, from 5 feet, they all look the same. The operator can't tell the difference between a roll of propylene, a roll of polyester, and a roll of polystyrene. They're all clear. They're all 56 inches wide. They're all on a 5-foot diameter roll with a 3-inch core. So to him, they all look alike. So can you imagine his confusion when he puts up the polystyrene first and he gets a dyne number that basically goes off the chart, and the next job he runs later in the shift is a polypropylene, or maybe the next day it's a polypropylene, and he can't get the dyne level above 34 with the same power density. You can see where the confusion comes in and why the default is, hey, there's an equipment problem here, because yesterday the treater gave me 60 dynes. Today the treater gave me 34 dynes. Got to be a problem with the treater. Well, the point of the slide is just to illustrate that while it's possible from time to time the treater can be a source of concern there, realistically, you got to take a look at the type of film you're treating and then the characteristics of that film. So again, as we show here, some films respond more aggressively to small amounts of treatment. So for example, let's take two polypropylenes, right? We have a BOPP and an OP and a standard cast polypropylene. Well, again, you start with your initial dyne level. On the BOPP, we apply a given watt density of 1.1 and we get a certain result. At the same watt density on this cast polypropylene, at the same watt density, we're not even getting anywhere near that same result. Here's where the confusion lies, folks. Are they both polypropylenes? So when you try to troubleshoot this with somebody, or you're talking to a colleague in your plant, or maybe in another plant, and you're trying to figure out why something didn't meet your expectation, make sure you understand the terminology. Are we referring to the film being treated as a cast polypropylene, which might have one characteristic, or are we dealing with an oriented polypropylene, both biaxially or just a standard oriented polypropylene, single orientation, that might exhibit a totally different characteristic? And so in this slide, you can see what happens. And of course, if you look at the slide, you can see where the confusion comes in and why things don't appear as simple as sometimes people assume they are. So again, watt density and cost. This is really important and interesting. I'm going to cite an example as close as I can to an actual conversation I've had with folks over the years, and some of you can relate to this. So the conversation goes like this. I need a corona treater, and here's the application. I have a particular film, it's a particular width, it's on a printing press. The film comes to us pre-treated. My customer tells me that they have to have a 56 dyne on this material, and that's part of their spec to us. You know, we're converting the film for this end user, and the end user tells me I have to have a particular dyne number. And so, of course, in my part of the conversation, I'm asking questions about, well, what are you doing? Are you printing? Are you coating? Are you laminating? And then I'm focusing on the answer of that, and then I'm trying to understand that answer and put it in context with the piece of equipment. So it goes like this. I'm water-based printing. I'm using a polypropylene film, and the end user is telling me I need 56 dynes. Well, I get the water-based printing and I get the polypropylene. The disconnect is 56 dynes. I don't know about you guys, but I don't know any water-based printing application in any film that requires 56 dynes for water-based printing to work. And so what happens here is there's a disconnect, right? The disconnect on that end customer's viewpoint is a dyne number equals success, and that dyne number has to be high in order for the ink to be successful, rather than saying the ink is going to be successful if A, it wets, and B, it passes a particular peel adhesion test, which is really the two things they should be looking at, right? Because the dyne level after the material is printed and rolled up and sent on for further converting is immaterial. But put yourself in this position. Let's say you're the person responsible now for this application where somebody is demanding you have this high dyne number. So you go back to your corona treater supplier, Enercon or whomever, and you tell them, I need a treater that generates 56 dynes on polypropylene film. Well, even if it's possible, look at what impact this has on the watt density. What did we say earlier? Typical watt densities for corona treaters are 2 to 3 watts per square foot per minute. Well, in this one example, you could be somewhere between 7 and 10 watts. So let's run this example out to its end use. You can see the example here. So at a 5-foot web, single side, 500 feet a minute, a watt density of 2 gave us a 5 kilowatt power supply. If I have to take that watt density and multiply it times 3 or 4 in order to meet these higher watt density numbers, your power supply just went from 5 kilowatts to 20 kilowatts or 30 kilowatts. And now we're only talking about just half of the treater, right? Corona treaters are made up of 2 pieces. The corona treater station, the part that does the treating, and the corona treater power supply, the part that does the power generation. So now you've got a 30 kilowatt power supply, and you have a corona treater that's got to dissipate 30 kilowatts, which is a big corona treater. Okay, it's going to be a very big and expensive corona treater. And all to meet what? What are we meeting? We're meeting a requirement that isn't even needed. And so really, what happened here? How did our conversation sort of get tippy and awkward? Well, it got a little awkward and off kilter because of really a lack of basic understanding of what we're doing when we corona treat the film and what's actually required. And so sometimes if you are in this experience and you have another colleague or maybe a salesperson or somebody up the chain that's a little further away from the actual process, make a demand of you of that, sometimes you're going to have to step back and do a little bit of education with that person to get them to understand that, first of all, the process isn't linear, and there's multiple pieces in the process that doesn't require it to be linear. You know, the ink chemistry doesn't require, in this example, a 56 or 52 dye number to be successful. And so requiring these giant watt densities, or giant dye numbers, really, which then in turn may require giant watt densities, really do you a disservice and are not useful in terms of economics or in terms of, you know, best use of capital, or for that matter, you know, a treater of this size, just trying to, if it's an existing piece of equipment, you know, just trying to find a home for it, just trying to find a space for this equipment would be pretty hard to do on an existing asset. So keep in mind, dyne levels and watt densities don't always match, and really adding a watt density, high watt density calculation to your assessment really can cost you a lot of money and effort that there's really no payoff for in the future. So just to close the loop on this, just to sort of put a ribbon around this topic, power supplies of that size require bigger treaters, which usually then require bigger electrode assemblies, more electrode assemblies, larger frame weldments, larger ground rolls required to dissipate all this heat we're now generating, and of course things like airflow, exhaust rates. I mean, it's a domino effect, folks. Once you make these large requirements, everything along the train just kind of blows up on you, and you end up with a very, very large and top-heavy piece of equipment that can cause all kinds of downstream other requirements that maybe weren't calculated in your budget. So Mark, can you just change the, yeah, there you go, thank you. Sorry, I got a little slide here that didn't come in. So do you need a higher watt density? Do you really need a higher watt density? Really think about this. Is it because somebody said, I need this big dye number? Is it because somebody a long distance away from the application asked for it? Have you actually thought about the application in those terms? Have you defined what your goal is in the application? These are all the questions you have to ask in order to make sure that the corona treater equipment you're asking somebody to supply you is appropriate for what your application is. Go ahead, Mark.
Sure. So, Tom, thank you for those insights. We're gonna go to a summary and then get to the questions section next. We already have some questions on the board, and feel free to continue to send them in. In the meantime, I'm just going to send out a second poll based on the information that we provided you today. If you can answer this, we'll leave this open for about 30 seconds, and we will move on to the summary. Got about 50% so far, so they're still coming in. We'll leave it open for a little while longer. We appreciate your participation in this. We are up to 80% of our audience. And we are going to close the poll now. Thank you for your feedback on that. So in summary, some of the things that Tom covered today. Films respond differently to treatment, primarily for reasons inherent to the film type. Similar films can also respond differently because of additives or surface contamination due to age or storage conditions. Your specific application requires its own recipe for success. This means meeting your dye level goal is a good indicator of your chances of adhesion success, but the true test of success is how you actually test for adhesion in your operation. Based on the parameters above of dye level and your adhesion test, you can determine the expected watt density that will best meet your application's needs. We'll now switch over to our questions, and as I said, we have quite a number coming in. So here's a question: how long would corona treatment be effective at the surface of Kapton polyimide film used for printing later on?
Well, it's a great question. Typically, Kapton films are actually pretty receptive to corona treatment, and the dye levels are relatively stable. Although that said, you know, the devil's in the details there. You know, so it depends on what kind of chemistry you're applying, whether it's a solvent chemistry or water-based or energy curable, whatever the case. But just in a general way, it is Kapton material is pretty responsive to corona treatment.
Here's a question regarding humidity. Is the impact more on high humidity environments or low, or both?
Well, high humidity has more impact on the, not necessarily on the dye level of the material, but the humidity in the air has more impact on the performance of your equipment and the maintenance of your equipment. So for example, during the winter time, if you're in the southeast, let's say for example in the United States, in the wintertime the air is more dry, and likely your corona treaters don't suffer many maintenance or issues relative to that. In the summertime, when you have high humidity, high heat conditions, corona treaters tend to have more maintenance and service trouble because all of that moisture collects dirt, debris, additives, all the stuff that we're chasing off the film collects on the treater and requires you to clean it more often. It doesn't necessarily have a negative impact or a performance impact necessarily on the ability for the treater to treat the film.
Is there a limitation on how many times a film can be corona treated?
That's a great question. I've never heard that one before. Not to our experience. We have not had a direct exposure to that, and I'm not aware of any. I never heard of that, so I don't necessarily think there is an issue there.
Does the gapping between the treater bar and ground roll have any effect on watt density or dyne level?
Now that's again a great question. I'm glad that was asked because I get this question all the time. No, the air gap has nothing to do with respect to the watt density or the or the dyne number of the process.
What is the optimal way to measure dyne level on polypropylene or polyethylene plastic film?
Well, it's a great question, and Mark, we may have to put this information out there again. You know, so the question is the best way to do dyne testing. Many of you now are doing dyne tests in a very convenient manner, thereby using a dyne pen. And dyne pens can be very useful in terms of simply determining what side of a roll of pre-treated film is treated, right? Because as my example stated earlier, you got this, you know, 56-inch roll of film sitting on the floor, and you're trying to figure out how to load it on the machine, and you want, let's say, the treated side to be out. Well, how do you know what side's treated? So you take the dyne pen and you go over there and you mark it. But if you're, and that's fine for that purpose. But if you're really trying to tighten down your dyne testing, a dyne pen is not the right tool. The tool to be using there are actual dyne solutions and Meyer rod. So you take a number 4 Meyer rod or number 6 Meyer rod and use dyne solutions. And there's a test method out there for this. Mark, I think, refresh me on this, but I think it was a tappy test method that was with the Meyer rod. If I'm
with the ASTM.
Yeah, I think so. We have, and some of you can email me and I'll send it to you. I have the paper, I just don't have it in front of me. But there's a paper that Tappy did some while back on this test method using a Meyer rod method, and it's really effective. We kind of went away from it over the years for some reason, maybe just due to convenience of the pens. But in any event, this Meyer rod dyne solution test method is a better approach to take, and it will make your dyne testing more consistent if you choose to use it that way. For more information on this, more detailed information, send me an email. I'll happily respond to you and send you the paper.
So Tom, we've got a couple of questions related to the thickness of materials and how that might affect treatment or watt density, if at all. And also a specific question on a 12 micron PET seems to be problematic for someone with a printing application.
Well, typically, for most film converting applications, now notice I put a little qualifier in there, film converting. I'm not talking about sheet, I'm talking about film. So films meaning anything from, I don't know, 0.5 mil to, let's just say 20 mils, okay? Let's pick a wide range. In that range of common films and converting applications, the film thickness doesn't really play a role at all. It doesn't matter to the success of the treater. We don't look at those film thicknesses and adjust our watt densities or adjust power or anything based on that thickness. So in that respect, it doesn't matter at all. Now, if you're attributing, and it's being specific here on this 12 micron polyester to what was it, 24 micron polyester, in that specific example, I'm not sure what the problem is, but if the example there is saying, well, at 12 micron we get a good result, at 24 micron we don't get such a good result, you may want to look at things in that case like wrinkling or puckering or some film malady that would cause backside treatment, maybe due to wrinkling. So for example, let's say the 12 micron material in that example has an issue, whereas the higher doesn't. Well, in the lower example, you may not be running much web tension simply because you can't. You break the web potentially. And in that example, you might find air building up behind the web, getting some backside treatment, so therefore treatment on the top side, the side you want to convert, is not as good, and therefore your end result isn't as good. On the opposite end, where you can apply a little more web tension, maybe the result is better because you're not getting any backside treatment, and so therefore your results are more to your expectation. So typically, film thickness of itself doesn't affect anything. However, film thickness and conveyance issues can have an impact, and maybe that's an area to investigate in that one example.
All right, here's a question. Can you have a dyne level that is too high?
Well, that kind of goes to over treatment. You can have dyne numbers that are high, and that number, not because of the number, but because of the energy that got put into the film to get that number, causes undesirable effects. So for example, let's say you take a polyethylene film, you normally treat it to 40 dynes and at a moderate 2 watt density. Somebody decides that they want to triple a watt density, and when they do that, now the material starts acting funny. It'll start to gather a bunch of static, or it'll pucker, or it'll wrinkle or something. And as a result of that, the dyne number went way up, if you did a dyne test. But really, that's not what you're concerned about. Because you apply so much power to the web, the web itself kind of reacted in a negative way, thereby causing you other application problems. So in that particular sense, one could say, yeah, a high dyne number caused this problem. It's really the power that we're applying to get the high dyne number that's causing the malady. So typically dyne numbers in and of themselves don't cause the problem, but the correlating effect of applying the power to get the high dyne number causes a problem.
So Tom, we have a question on calculating the watt density level when you have a segmented treater, for example, a 600 millimeter wide treater where they're not treating the 200 millimeters worth of the film. Do they calculate it by electrode width or the active electrode width?
It's all, in that case, when you have a segmented electrode, you're always going to calculate the watt density based on the active amount of electrode width. Always the active amount.
Here's a question on running copolymers, such as a polyethylene, polystyrene substrate. How can you assure surface uniformity? Well,
surface uniformity on a corona treater has really less to do with the type of material, whether it's a copolymer, a homopolymer, whether it's a lamination, whatever the structure is. From a uniformity standpoint, the treater doesn't care. Uniformity in corona treaters are typically as a result of the geometry between the electrode and the film. So if the electrode gap between the film and the ground roll is uniform, meaning that up and down it's uniform, in the web direction it's uniform, the end result, meaning the dyne number in this case, it should be uniform. If the electrode is canted or off adjustment in some way or another to where the corona can be closer in one area than in another, the corona is always going to go to the path of least electrical resistance in that example, which means you're going to get more energy on one side of the web than on the other. And when you do a dyne test, you might find then that the dyne level is higher on one end than on the other, and that's not really attributable to the material composition. It's attributable to the mechanical setup of the corona treater typically.
What is a typical high-end speed for treating high-volume manufacturing environments?
Well, you know, that number's creeped up a lot over the years. I think now we've had applications where we're crossing that 2,000, 2,200 foot per minute number. Certainly, it's not common, but it happens. More and more on new applications, new lines, we're seeing values up in that 2,000 foot per minute range.
Does the length that a corona treatment, the length of a corona treatment effect lasts depend on each individual material?
It depends on, yeah, right, how long the treatment is the decay rate. If I can rephrase that question, if he's asking what is the decay rate, is the decay rate, dyne level decay rate change with the type of material? And the answer to that is yes. Different materials have different decay rates. So I'll give an example. In polypropylene film, for example, the decay rate from 40 down to say 32 may be quite steep and fast. Whereas on polyester, the decay rate from 56 down to the mid 40s, let's say, might take a while. It might be 6 months or something. So yeah, the film itself, the film composition and what's in the film certainly has an impact, or a significant impact, into the dyne level decay rate.
How do you control backside treatment?
Backside treatment is a common malady in our industry. It's one of the most commonly asked questions I get, and it's the simplest thing to solve. First of all, you have to know what it is. Backside treatment is simply ionized air behind the web. So for whatever reason, whether you have a bag in the film, whether you got dirt on the ground roll, whether you have a loose web tension, whatever the reason, you got air that got beneath the web, air between the back of the web and the ground roll. And when that air gets under the corona treatment, you're going to ionize that air, like we learned earlier. Corona is just ionized air. You're going to ionize that air, and you're potentially going to get backside treatment. And how you control it is through web tension. You control it through making sure film is flat. On high-speed lines, many times corona treaters have nip rolls and drive systems, which allow us to control the web dynamics as it goes through the treater, thereby controlling things like backside treatment.
Well, we're just coming rapid fire at you, Tom. Can a polypropylene spun-bound nonwoven be successfully treated for a printing process?
Well, that's pretty specific. I can answer in a general way. Yes, you can corona treat that prior to printing.
What's the difference between a bump treater and a full-fledged corona treater?
Well, bump treatment really refers to, you have to start someplace with this example. So we're going to start here. We're going to assume that it's a printing application, and then we're going to assume that the film being put into the printing application starts at 36 or 38 dynes, which typically that dyne number wouldn't be good enough for a water-based printing application. Maybe for water-based printing we need 40 or 42 or 44, it depends on the ink chemistry, but somewhere in that range. So bump treating refers to taking a 36 or 38 dyne pre-treated material and just bumping it 2 to 4 dynes. And so the power required to do that typically would be small, low. So depending on the speed and the width, the exact details of the application, you might only require something like a 5 kilowatt power supply or less, versus on a blown film line, for example, when they made the film, that material being what it is may have required a 10 kilowatt power supply or something, based on their running conditions. So that's kind of the difference when you talk about bump treaters.
What are the parameters to ensure a good maintenance of the treater?
Well, really, it's just, again, like a lot of things, it's just paying attention. Just visual inspection. You should be visually inspecting that corona treater, and the areas of visual inspection that are required most are surrounding the electrode. So without respect to the type of electrode, whether it's a metal electrode, segmented or fixed, or whether it's ceramic electrode, it doesn't matter. This all applies. Inspect the electrode. Make sure there's no dirt, debris, carbonized film, anything like that. Make sure none of that stuff is on the electrode. If you see some on there, clean it off. All of these things, folks, that we corona treat, they're all carbon-based. And the corona treater's job, one of its jobs, is to affect the surface. And so we're going to chase some of that stuff off the surface to get the surface ready for converting. And during the course of that, some of those materials will plate out on the electrode or the surrounding area, and they will revert back to their original form, which is carbon. And if that occurs and you don't clean it off, carbon is conductive. And as you guys have heard me say this a lot, and I'll repeat it again, corona always goes to the path of least electrical resistance. So if you get a carbon spot somewhere, that carbon spot looks like a better path to ground than the ground roll, and so it'll arc to that carbon spot until such time that the treater shuts off. So you really got to clean the electrode, make sure you don't have any burnt pieces of film, additives, dirt, debris. Clean that electrode and look at it regularly, monthly, sometimes even weekly, depending on your application.
This is a question back to thickness of material. If there's not a relationship to the watt density, if I run the same watt density on a film that's 0.5 mils and 20 mils, should I see the same results?
If the film is the same, yes. So for example, if I had, what's the range we have here? 20 mil?
5 and 20.
5 and 20, yeah. So if I had 5 mil polypropylene film and had the same additive or color additives or whatever package is in there at 5 mil and at 20 mil, and I ran the same watt density, I should get the same result.
If dyne levels do not guarantee adhesion, what are some of the best tests for adhesion?
Well, everybody's got their own test method here, but again, depending on what the process is, so depending if it's printing or laminating, so let's pick a printing application because that's the simplest to describe on a webinar. Typically, you would use a tape test. So your material's printed, it's treated, it's printed, it's cured, it's wound up. Now you take a sample in the lab, and you might place a sample in a holder, and you take some specific tape, and you apply the tape in a proper way to that printed surface, and you peel it off. And if you get ink pick, meaning ink doesn't stay on, it may fall out of a specification you have, that would be an indicator of failure. And that failure can be for various reasons, one of which could be the corona treater or how the corona treater was used. But that would at least get you started down a path of looking for what changed. There are variations of that tape test. There's all kinds of resources out there for you to look at that, but that is just one example of a test method that you would use for determining adhesion in a printing application.
Is it possible for a film to have too much additives to bloom to the surface when any amount of treatment will not work, making the material unusable?
Usually it's that and a combination of age. So if the surface of the material has so much additive on the surface and on top of it is really old, sometimes that's a pretty deadly combination to where you just can't, it just doesn't respond to much of anything. In today's world, because the film makers, the people who make film are really good at their job now, and they are very diligent about costs, and these additives that we talk about in a casual way are expensive. And so it's not like the old days where they would apply these additives in sometimes a little willy-nilly way. Nowadays, that doesn't happen. And so the additive loading and the amount of additives that are in the surface usually are pretty tightly controlled, and therefore it's unusual to have a surface that has so much additive on it that it can't be treated. But there are exceptions, and it does happen from time to time.
I believe this would be, again, for a segmented application. With the same watt density, with the same power, will the watt density change if I remove or add electrodes or remain the same? My question is more, if I remove the electrode and then it says move them up, is the power more concentrated within the remaining electrode?
Well, the power will be more concentrated if you do that. The watt density won't change, right? Because the watt density is based on the power didn't change. So the amount of power is the same. All you did was either take and put more electrode segments in, or took electrode assemblies out. So really what you did there, if you took them out, you increased the power per unit area of inch. Let's say where you're measuring treatment area in inches. So if you applied 1 kilowatt over 10 inches, and that was so many watts per inch, and now you halved it, but you were still applying the same wattage, well, you just doubled the watts per inch. So the intensity of the discharge would be higher. Whether that would necessarily net a result of a bigger dye number or not, I'm not sure. It depends on the film and the particulars, but it certainly wouldn't affect the watt density.
We have got a couple of questions related to atmospheric plasma versus corona. If you could speak towards some of the attributes and specifically, is one better than the other?
Well, first of all, I would like you all to keep this in mind when you evaluate surface treating equipment, whether it's corona treating equipment, gas flame treating equipment, atmospheric plasma treating equipment. There is no good, better, best. Please remove that from your thinking. There is no such thing as good, better, best. That doesn't work that way. The equipment that you use for these applications is in line with the material and the application. So I'll give you an example. Let's just say we're on a printing press again, and we're running standard converting grade film. So meaning we're running polypropylenes, polyesters, polyethylenes, polypropylenes, and we're running in typical speeds, 500,000 feet a minute, water-based printing, nothing out of the ordinary. Could you use a flame treater, an atmospheric plasma treater, or a corona treater? You could use all three. You could use any one of those three, and they all would result in a good ending for you. The downside is you would spend multiples of more money for the flame and the plasma treater without getting any benefit outside of the corona treater in that example. So in that example, a corona treater is really the best result, not because it's the only thing that does the job, it's just economically and functionally does the job for the best economic capital. Now take the same example. Let's say we have the exact same machine. We're going to try to print Teflon film. Well, corona treaters don't do very well with Teflon film generally. So in that case, an atmospheric plasma treater actually would make a lot of sense because the atmospheric plasma treater has the ability to change various gas chemistries, add and delete things, which therefore give you a discharge that's more suitable for working with this PTFE surface that we're now dealing with. So my point of making this example is just to show you that it's the application that drives the equipment. What is your film? What are you trying to accomplish? And then when you look at those things and you contrast it to the type of piece of equipment, you're going to pick the one that works the best based on your application.
All right, it looks like we've got about 2 minutes left here on the webinar. We'll get to a few more questions. You guys have been great. These are fantastic questions. If you enjoyed the webinar, if you learned something from it, you see Tom's email address right there on the screen. Go ahead and email him and let him know your feedback, what you liked about it, what else you'd like to see us work on in the future. We'd really appreciate it. Can corona treating a polyliner assist with inkjet printing on the liner?
It can, and it can do it simply because that polyliner does not have any functionality as it's made now. So if you corona treated that, you would be adding some functionality which would be comparable to the actually the inkjet printing that we're working with.
What's the pros and cons between a bare roll and ceramic roll application?
Okay, that's a great question. We get this question all the time. So bare roll treaters are defined as ceramic electrode treaters and just a bare aluminum or maybe a conductive ceramic coated roll. And they've been around for a long time. Enercon introduced that technology back in the mid-'80s here in the United States. They're very effective for all kinds of things, principally among them, if you're using if your application is treating, say, a foil off a secondary unwind to where you're just running this metallized material, this conductive material all the time, bare roll treaters are awesome for that. That's really their sweet spot. That's what they're intended to do, and they do a great job. Now, what's happened over the years is this bare roll technology has been advanced, and we now, since the early 90s actually, have been using this hybrid technology. And the hybrid technology combines ceramic electrodes and a ceramic coated roll. and virtually 98%. In fact, the slides you see that you've seen on this converting equipment in this presentation, all of those pictures show this ceramic electrode, ceramic coated roll system. That's a sort of hybrid system that's used. And why it's used is because it has a lot of benefit relative to treating all kinds of film. It has dyne level benefit, meaning that we get some bump in dyne level for the same given unit of power versus a bare roll treater. It has some film handling benefit relative to treating some thin gauge film. And on top of it all, it can treat conductive materials. And so it really is the best of all particular corona treaters sort of wrapped up into one. The one thing those systems can't do is if you had an application where you require lanes of treatment, meaning I treat 6 inches, I skip 2 inches, I treat 6 inches, so forth. Yeah, that system can't do that. Then you have to look at a different type of treater. But the difference really is these bare roll systems versus a hybrid system. Hybrid systems give you, ceramic roll systems give you much more flexibility and really are the standard really in the converting business.
All right, thank you, Tom, and thank you to our audience. We'll be sending all of you an email with access to the recording of the webinar as well as the presentation slides. In the meantime, if you do have additional questions, please reach out to us via our website or directly to Tom. Thank you again, and that will conclude today's webinar.